Okay, so today we are going to focus on how much can dissolve, how much is dissolved, and how we describe that. What affects how much it dissolves, and how we can describe those different types of solutions. Okay, so where we finished off yesterday was right about here, right? That we had the equilibrium between molecules dissolving and molecules turning back into a solid. Okay? Okay. So when you're at that equilibrium, it's going to look like nothing's happening. There'll be solids sitting at the bottom. Won't look like, and it won't change. And you'll say, well, there's nothing happening. But no, that's not true. What's happening is it's dissolving and it's undissolving, but at the same rate, so you have the same total amount of stuff on the bottom. The atoms themselves are not the same. And the way they track that is, if you put if you have sodium chloride, you make a sodium chloride solution, and then you throw in a piece of chlorine that's radioactive. Okay? And you only put it in the solid. And then you wait a day. When you come back, that radioactive thing will be both in the solid, in the liquid, in the same amounts. This tells you that they're going back and forth. We just don't get to see the individual pieces going, but they are moving. That's how they know, is because they've tracked the radioactivity. It was in the liquid, then it's in the solid, then it shows up in the liquid again. That's how they know. So, equilibrium is rate of dissolving equals rate of crystallization. That's what happens at equilibrium. Rate of dissolving equals the rate of crystallization. So that's why there's a limit to how much you can dissolve. Because as you get near that limit, it starts undissolving really fast. And so, you've already written all the other stuff yesterday. Look at the last slide. This is this slide. That was the previous slide. Yeah. Why there's a limit to how much you can dissolve. Okay? So we have to describe solutions that have dissolved. Okay? So we talk about solubility. Solubility is the maximum, it's a number. It's a number with a unit. It's the maximum amount that you can dissolve in a set amount of solvent. I mean, can I dissolve 2 pounds of sugar? Well, it depends on if I got a gallon of water or a swimming pool. Right? I need not just the amount of sugar, but how much stuff I'm pouring it into. So you're always going to have a couple of units. One for how much is dissolved, the grams. The other for how much it's dissolved in per liter or per 100 milliliters. And it's a number you can look up. And if the solubility was 10 grams per 100 milliliters, and you put in 5 grams per 100 milliliters, it would dissolve. You put in 15 grams, 10 will dissolve and 5 will sit on the bottom. Eventually. It'll take a while to get there, but that's where you're going to end up. Okay? Once you have one that has got the maximum amount of solid, we call that solution saturated. Because when you come in from the rain and you say your clothes are saturated, that means they won't hold any more water. Saturated. Can't dissolve any more stuff. So a saturated solution has the solubility number of grams dissolved. You will always end up with a saturated solution as long as you end up with solids sitting at the bottom of the container. Because that means you've got as much as you can and it's able to interchange. You just got to give it some time. It may take a while to get before it's completely saturated, but if you got solid sitting there, you know it's saturated. Okay? If you don't have solids sitting there, we've come up with the creative term unsaturated. Unsaturated means it can dissolve more solute. There's just room to hang on to more, that you haven't filled up all the water molecules. And you would think that these two would be the only possibilities. You've got all you can, or you don't have all you can. But there's another situation that shows up temporarily called supersaturated. It's an unstable situation where a solution is temporarily holding more than it can hold long term. And if I put in one seed crystal, the extra will come out. Supersaturated happens with chemicals that make complicated crystals. That random motion together, bringing all the pieces together to make that first crystal, is unlikely. But once you get the first one formed, then you've got the pattern to build off of. And all the other ones know, all the other ions know where they're going to fit in. Right? Because there's a pattern to the crystal. Once you start the pattern, everybody can fill in. So, got a solution of sodium thiosulfate here. First of all, I have to tell you it's a solution. You can't tell by looking that there's anything dissolved in here. That there's a liquid, you don't even know if it's water. But this is a aqueous solution of sodium thiosulfate. Saturated, unsaturated, or supersaturated? Okay? And how do you know? There's no solid at the bottom. But if I had a saturated solution and I just picked it up and left the solid behind, would the solution still be saturated? It would, wouldn't it, right? It still couldn't hold any more. So just the fact that there's nothing on the bottom can't tell me whether it's saturated or not. The only way I can tell whether it's saturated or not is to add a crystal. If I add a crystal and it's saturated, that crystal will just sink to the bottom because it can't dissolve. If I add a crystal and it's unsaturated, give it some time, it's going to dissolve. It's going to go away. And if it's supersaturated, lots will come out. So I'm going to put a crystal in. So I've got a crystal of sodium thiosulfate here. Okay. Put one crystal in. It's growing. Okay, so the crystals are all growing long, but you'll notice they're long and needle shaped. They're complex. They're complex crystals, hard to form. Okay, it's it's actually still growing crystals. Mm-hmm. But we now know for sure that this was supersaturated, right? Everybody clear? Okay, how did I do this? It's supersaturated at this temperature. The way I made it was, I put it in hot water, dissolved a lot of stuff, and then stuck it in cold water and cooled it off. And a lot more can dissolve when it's hot. So I dissolve a lot, then I cool it off, and the extra is supposed to come out, but it can't make that first crystal. Once it gets one crystal, it can make the rest. Does that make sense? So it's not a stable situation. So That's how we can talk about them as how much they're holding compared to how much they could hold. What affects how much will dissolve? Well, for solids dissolved in liquids, when you heat them up, they usually dissolve more. That's how I'm making this, taking my supersaturated solution, I'm going to turn it into an unsaturated solution. This one here I think will actually work a little bit better. I had to make a lot of them to make sure one of them would work. 3, 2, 1. There's a little crystal at the bottom, but actually on this one, you actually see the line where it fell through.
Oh, I see.
Where it fell through the liquid, left its trail, like a little spiral all the way down the middle of it, that where the crystal touched, it could make new crystals grow. Okay? So it hadn't gotten big enough they're starting to fall, but it was just a string right down the whole length of it. Okay? Because how much of this do you think is water?
Many.
There's probably 4 milliliters of water in here.
So many.
Sodium thiosulfate. Yeah. Okay, so it's still supersaturated. They're still coming out of solution, actually. Okay, we'll just let it sit there and see how much I can get out of there. Okay. Okay, so, but now the first one, this is not a guarantee. It's a usually. It's a safe bet, but it's only a usually. There are some things that, some sulfate compounds tend to be less soluble when you heat them up. Okay. But for gases in a liquid, as the temperature goes up, the solubility goes down. The gases are less soluble at high temperature than at low temperature. You can dissolve less gas. You've seen this if you've ever put a pot on to boil. Put a pot on to boil, you'll notice that first there's a set of bubbles that grow on the outside at all the whole surfaces, right? That's because the water is less able to hold the gases at high temperature. That's the dissolved oxygen and carbon dioxide coming out. Because those bubbles form and then go away, and then you get completely new bubbles at the bottom, and those bubbles are steam. But the first set of bubbles you see when boiling water is the carbon dioxide and the oxygen coming out, all the dissolved gases. Okay. This leads to something called thermal pollution. Actually happened when I was in high school. Actually, it was an issue for a power plant that they just opened up in our neighborhood. Not our neighborhood, but in our TV viewing area. Because I was in the middle of nowhere, so there wasn't really a neighborhood. Okay, but they opened up a power plant, and they always put power plants near sources of water. So they put this one by a river, okay, and they turned on the power plant and they ran it, and somebody noticed that all the fish and all the plants downstream from the power plant were dead. Okay, say, whoa. So they said, hey, power plant, you're polluting the river. And the power plant says, oh, okay, this is what we do with the river water. We take the river water in and we put it into a pipe, and then we pump it through the factory in that pipe as a radiator. So all it does is absorb heat while it's in the power plant, and then we pump that water back out into the river. It never touches anything but pipes. Okay, and actually, it's only when we pump it back in, it's only 5 or 6 degrees hotter than it was when we took it out. Okay, so what's happening? Well, it was more than 5 or 6 degrees hotter inside the building, and those dissolved gases came out. So when you pumped it back in the river, there was nothing for the fish to breathe. There was nothing for the plants to breathe, because they breathe the dissolved oxygen, the dissolved carbon dioxide. So it killed all of the plants. Yeah.
Wait, so if there's no oxygen in water, how's it water?
No, dissolved oxygen, O2. O2. Yeah, the fish don't take the oxygen off of water. That takes a lot of energy. Okay.
Fish would have to be very strong water.
Yeah, had to partner up with some electric eels. The So the power plant said, okay, we will cool the water before we put it back. So they built next there, they built these big ponds right next to the power plant. The water came from the river, it went through the power plant, got hot, they pumped into these ponds, let it cool, and then pumped the cold water back into the river, and all the fish and all the plants died. The solubility went up. It was colder, more could dissolve, but where do you put the pump in a pond? At the bottom. That water at the bottom, how much air is it touched? Zero. The only place the water's touched the air is at the top. That's the only place it can dissolve in. It's a surface area problem. Okay? It was cold enough to dissolve more. It was mid-70s. It was cold enough to keep more oxygen, but you didn't actually touch any oxygen. So now, if you go to power plants that are on those things, what you'll see is they don't just cool the water and pump it back in. They either spray it through the air. Use a hose and spray it up through the air so you get cold water spraying through the air. Air and water touching everywhere, the gases are going to dissolve. That'll work. Or they let it tumble down a waterfall. Because you got to have the cold water and it has to mix with the air. It needs both pieces. It's got to touch the air. The cold water means it can dissolve more. Mixing with air means it gets to dissolve more.
Yeah.
Okay. Now, for gases in a liquid, as the pressure affects solubility, it doesn't affect solids, it only affects liquids. Changing the pressure doesn't affect the solid, but it does affect gases in a liquid. It doesn't affect solid in a liquid, it doesn't affect liquid in a solid, it affects gases in a liquid. And as that pressure goes up, the solubility goes up. The way of thinking about it is back to that equilibrium idea. The way the pressure goes up is the molecules are hitting the surface of the water more often, right? And every time they hit the surface, they got a chance of being dissolved. So the higher the pressure, the more likely they are to be dissolved. So as the pressure goes up, the solubility goes up. That's why they give oxygen to patients in hospitals. Well, there's oxygen in the air. Why do they give a tank of oxygen? Well, because the air is only 20% oxygen. A tank of oxygen is 100% oxygen. So you go from 0.2 atmospheres to 1 atmosphere, 5 times the partial pressure. You can dissolve a lot more oxygen. You got 5 times the partial pressure. About, if you saw Henry's law, about 5 times as much. Okay, so it makes the oxygen dissolving into your blood more efficient. Okay. Okay. As the pressure goes down, solubility goes down. You've seen this every time you've opened up a 2-liter bottle of soda. Before you open it, it's got lots of pressure. You open it, it's got less pressure, and you get to see the bubbles form inside. Lower pressure, less soluble, you see bubbles. And this leads to problems for scuba divers. Anybody here take a scuba?
I did.
Okay, then you know about our friend, the bends. Okay, so if you're a scuba diver, one of the things they teach you is you don't just dive down and come back up. Okay, when you dive down, you have to time how long it took you to get down, how long you stayed down, and then on the way up, you got to stop along the way. Say on the way up, you stop here for 5 minutes, you stop at this depth for 5 minutes, you work your way up gradually. Why? It's because of how the regulator works. Okay, so to breathe, our lungs have to expand, and we don't have a muscle that expands them. We don't. They just naturally expand. Okay, but as you dive deeper, well, and actually, so that's how constricting snakes kill. They don't squeeze; they just hold.
Yeah.
They wait for you to exhale, then they tighten up,
Yeah.
and then you can't inhale because your lungs would have to get bigger.
That's why I have snakes, and that's why it takes them so long to kill them.
Yeah, so it's not. So that's how a snake kills is just wait for it doesn't let your lungs expand. Well, if you dive down, the pressure gets higher, right? Okay, and that pressure starts pressing on your chest. If you had 1 pressure air, but 2 pressure water, the air would go from your lungs into the tanks. That's not the direction you want the air to go. Okay, so the regulator, what it does is it makes sure the pressure coming out of that mouthpiece is bigger than the pressure caused by the water. So it can blow your lungs up. Okay, which means the deeper you go, the higher pressure that air is. Okay, so when you dive down there, at high pressure, gases are going to dissolve. Right? And mostly it's the nitrogen we're worried about. Then you come up. If you come up fast, the same thing's going to happen to you that happens inside a soda bottle when you turn the lid. You're going to make lots of little bubbles. Where? Every place there is liquid in your body. Lots of liquid. Majority of places actually in the joints. Got lots of lubricating fluid in your joints. So to relieve that pressure, people bend their joints. And which joints they bend? They bend everything. They curl up into a little ball and try to bend every joint as much as they can to relieve the pressure on those joints. That's why it's called bends. But along the way, it forms a bubble inside a brain cell. There goes a brain cell. It finds a bubble inside a nerve cell. Boom! Now that hurts really, really badly.
Yeah.
Okay. And it's going to happen where in your body? Everywhere. So you don't want all those bubbles coming out at once. So you come up, you stop, you let some come out slowly. Then you go up higher. Let some come out slowly. That's why you have to wait on the way up. Okay. On a bigger scale, I need to tell you a story about a lovely lake in Cameroon. It's called Lake Nyos, depending on who you talk to. It's a lake in the top of a volcano. You know, the crater of a volcano got filled up with water. Okay, so and right next to Lake Nyos is a little fishing village. Nyos Village, right there. So there's the lake, and there's the village.
That's no good.
Okay. Well, somebody came. Somebody went up to this, came to visit the village and found that every animal was dead. Every animal was dead. By animals, I mean every cow, every insect, every person, every dog. If it was in the animal kingdom, it was dead. But nothing was harmed. There was no sign of a struggle. There was no sign of a scar on anybody or anything. They just died. So what killed them? And the answer is that lake. Say, well, how can a lake kill me? Well, here's how a lake can kill you. Okay. So, here's the model of it. So you got the lake up here, right? This lake is deep, right? And a deep lake is going to be, the bottom is going to be cold and high pressure. Volcanoes give off carbon dioxide. And all that carbon dioxide is going to dissolve into that water down at the bottom. No problem, because you can dissolve a lot of carbon dioxide. Unfortunately, there was a little landslide on the edge, which made some turbulence in this deep, still lake and stirred up the bottom. So the water that was at the bottom got to the top, where it was warm and low pressure. And all the extra carbon dioxide came out. And carbon dioxide is denser than air, so it flowed into the valley and filled the valley 150 feet deep with carbon dioxide. It's like the bottom of a canyon, yeah. So filled from the bottom up and filled up with carbon dioxide. Once carbon dioxide heats about 15%, animals die. Because they can't, and by the way, you die with the idea that you're out of breath. Because the thing that triggers your out of breath, you feel like I gotta breathe, is carbon dioxide building up. So if it's in the air, you're gonna feel like you're constantly out of breath, and you're gonna die. Okay, so
I know.
Okay, so the clue was that the lake turned over. This was before. That was after. All brought up all those dissolved stuff up to the top. And so so it didn't happen again. People live in that village right now. Okay, to make it so it doesn't happen again, all they did was take pipes and put them down deep in the bottom of the lake. And they started pumping the water. Okay? Once you start pumping the water, as it gets higher, it's under less pressure. So the carbon dioxide comes out of solution, which means that area is now less dense. And it rises faster, which is going to pull more water up the bottom, which is going to make more carbon dioxide. Right? And this jet of water right here is not powered. That is just the carbon dioxide pushing the water out the top. So they're degassing the lake by putting pipes down and just letting them go. Okay, so there's another one just down the road from it called Lake Manoon, and it has the same type of thing, but not as much pressure. So they're at 203 meters at 600 feet deep. I said it was deep, 600 feet. Okay, that did not look like a 600 feet deep lake, did it? Okay, and this one's only 200 feet deep, so they don't have as much pressure. Yes, because it only goes up to 8 meters, only 24 feet. That's 150 feet.
The water on the right is not what I
Okay. That's the equipment for how they test it. Okay, but that first lake, that's how what it was in January 2004. After you get rid of the carbon dioxide, it stops coming up. And that's what it looked like in 2009. There wasn't enough carbon dioxide to keep the water flowing. 2001, March of 2014. Yeah, I have 3 of them. Okay.
That's good, I guess.
So that's good. So you do not want to be around one of these things. Okay, all because gases are more soluble at high pressure and low temperature, which is what you're going to find at the bottom of a lake. Okay, so I wanted to give you some interesting applications of this. Okay, this you'll find in your book. It's a graph of solubility. It's called a solubility graph. The bottom is temperature, so it's about how temperature affects how many grams of solute per 100 grams of solvent. Okay, you'll notice that as the temperature goes up, the dark lines tend to go up and the dashed lines tend to go down. That's because the dark lines are solids, the dashed lines are gases. Okay, but they do different amounts. Like sodium chloride is at about 37 at 0 degrees, and it's just short of 40 at 100 degrees. But potassium nitrate is 13 at 0 degrees, and off the scale by the time you get to 70 degrees. So potassium nitrate, its solubility really changes with temperature. Some are more affected than others. Okay. There's one dark line coming down. That's sodium sulfate. Some of the sulfates become less soluble as they got hot. So notice what I said, solids are usually, it's not a guarantee. Gases are always less soluble. Okay. Now, type of thing you could do would be say, okay, if I took a saturated solution at 30 degrees of potassium nitrate at 30 degrees and cooled it to 0, what would I see happen? Okay. Well, if I had a saturated solution of potassium nitrate at 30 degrees, that would be right there, right? So I would have dissolved about 46 grams of stuff, right? Now I cool it down to 0. In 0, it holds 13 grams. So what I would see is, as I cooled it off, solids start to form. And the pile of solids on the bottom would weigh 33 grams. See where I got 33 from? So you can see the most I dissolve here, the most I dissolve there. Okay? Does that make sense how to read the graph? Good. All right. So, that's about how much will dissolve. Oh, see, it did make more solid.
It's so pretty.
Yeah. Okay. So to measure solutions, this is about quantifying how much. Actually, first we're going to do qualitative words, then we'll end up quantifying. Qualitative. Okay. And the qualitative word for how much is dissolved is concentration. What is the concentration of the solution? And that concentration is how much you've got dissolved in a given amount of solvent. Again, you can't just talk about what you got dissolved, you also have to talk about what you've got it dissolved in and how much of that. Because can I dissolve a ton of sugar? Well, it depends on how much water I put it in. So concentration as a concept is about how much is dissolved. What is the concentration? It's like length. It's something you can measure. Now we are going to go to the adjective form of the word. Concentrated. A concentrated solution has a large amount of solute for the amount of solvent it has. A dilute solution only has a small amount of solute. Now, where people don't have problems with these ideas because these names make sense, right? Concentrated means it's got a lot of stuff. It's all concentrated in that spot. Dilute means it's all spread out. Got a little bit dissolved in a lot of space. But where people make the mistake is they get confused with saturated, unsaturated. They're completely separate questions. Say, what do you mean they're completely separate? One is about how much is dissolved. The other is about how much could be dissolved. Because you can have any combination. You can have a saturated solution that is dilute or concentrated. You can have an unsaturated solution that is dilute or concentrated. You can have any possibility.
Going back to the saturated, non-saturated, unsaturated, is that applied to fats and foods?
Oh, with that, what they're talking about is number of hydrogens. It's a double, unsaturated has a double bond. If you break that double bond, you can put more hydrogens on. So the double bonded one is unsaturated. Polyunsaturated means it's got lots of double bonds. That makes sense? And when you open up that double bond, it's got to open up so that they're across from each other, and you have a trans fat. That's where the word trans fat comes from, because you've opened up a double bond. But what I'm saying here about saturated, unsaturated, what I mean by separate, it makes sense that you could have a concentrated, saturated solution. That you've got a lot dissolved because it can dissolve a lot, but you can't dissolve any more. A concentrated, saturated solution. There's a lot dissolved. I can't dissolve anymore. Okay? How do I know I can't dissolve anymore? There's solid sitting at the bottom. Okay? It's concentrated, it's saturated. But I can also have a dilute saturated solution for something that doesn't dissolve very much. Only a little bit will ever dissolve, so I only got a little bit dissolved, but that's all I'm ever going to get. It is dilute, but it is saturated. It doesn't dissolve very well. I can have a concentrated, unsaturated solution. I've got a lot dissolved, but there's still room for more. See how they're different from each other? They're not this. It's what you're comparing them to. Concentrated and dilute are compared to relative. Saturated, unsaturated, there's a number you're comparing it to. Right? Did you forget that number or not? Okay, so the units. You saw that we had grams per 100 milliliters on the graph. That's one. Grams per milliliter, they give it to sometimes. Grams per liter. Although we tend not to work with liters of solution. Okay. You can use all those, but you need 2 units. And these are the kinds of units that you're actually going to see on the bottles of stuff you pick up and read, the ingredients list. Okay, they'll have those kinds of units. But we're worried about chemistry. And chemistry doesn't happen in grams. Chemistry happens in moles, right? So I need a unit for concentration that has moles in it. It's not completely new. I've talked about it a few times already. Molarity. Molar. Right? I've used those words before, right? HCl. When I gave you HCl in the labs, I said, this is 3 molar. It is 3 times as concentrated as the stuff in your stomach. I said those words to you, right? Okay, molar. Molarity is the number of moles in a liter of solution. So molarity means moles per liter. Because that means if I grab a liter of this stuff, I know how many moles I have and I can do chemistry with it. Or if I grab half a liter of it, I know how much stuff's in it. Right? Half of what would be in 1 liter. Symbol for molarity is capital M. And it's calculated by doing moles over liters, and its value is moles over liters. So that's the equation too. It's how the units work out, the units can substitute, and it's how the equation works out. So what is the molarity of a solution with 2 moles of NaCl in 4 liters of solution? So they want the molarity. Well, that equals moles over liters. Do we know moles? Yep, 2.0. Do we know liters? 4.0. Do we need a calculator? No. So that's a 0.50, 2 sig figs. Molar. Or you could write it as 0.5 moles per liter. Those are both saying the same thing. So see how I said it's the equation and the units. Extra super hard? Okay. Okay, let's get harder. So much harder. What is a molarity of solution with 3 moles dissolved in 250 milliliters of solution? Yes, you can. Let me bother you. Oh, you're really going to do that? No, you don't have to. Okay. Molarity is moles over liters. The number of moles. 3.0.
Wait.
They didn't give me liters. Hey, you can put milliliters down there, but it'd be wrong. It needs to be liters. And remember, to change from milliliters to liters, I just moved the decimal point. 1, 2, 3 times to the left. 0.25 liters. So 3.0 divided by 1/4 is 3 times 4, which is 12. Molar. Okay, well, that's not that hard. Let me kick it up another notch.
Yep, there it is. More.
You know what I was going to do next.
But wait, there's more.
Okay, 15 grams of NaCl occupy 75 milliliters. What is the molarity of the solution? Molarity is moles over liters. The 75, I can move it over 3 times and get 0.075. I don't have moles though.
You have grams.
I have grams. Hey, can we turn grams into moles?
Yes, we can.
We've done it once or twice this year. NaCl is 58.44 grams. 35.45 and 23 minus 0.01. That's the fast way to do it. 15 divided by 58.44 equals 0.26 moles. I put that 0.26 moles up there. And it's got to be moles over liters.
And then like converting.
Yeah, you could, but what you would done, the conversion would have been this right here. It is the same math. No, it's okay if you did it that way. It's the same math. I just did it in 2 separate problems. Okay, divide that by 0.075. And I get that this is a 3.4 molar solution. That real tough? Yeah. Math's pretty straightforward. Complicated equation. Molarity is moles over liters. Okay.
How illiterate I am.
Okay.